Alright, welcome to day 3. You might notice that it's 1 a.m. What ended up happening is that I actually did one earlier today, but I used the rm command incorrectly and deleted half of the video files that I was going to put together, and I thought really published that. I was like, that's not really fair. So I came back at 1 to finish the day's job, even though I really don't want to, especially because we have no easies. There are no easies that we can do, which is very green. Very, very green. But I'm thinking I might do one of the 1D dynamic programming questions, I believe. I think this is not a bad idea. Before I do that, I'm gonna look at some of these really quickly, just to remind myself what DP would look like. Okay, yeah, this is actually the question that I did earlier today. Yeah, it was pretty fun, but it took too long, so I'm here to redeem myself. So, what do I remember about DP? DP involves there's mainly two approaches. There's top-down, and then there's bottom-up. So top-down usually involves you will recursively call a method to solve for DP of something. When you get the result, you memorize it. And there are base cases that break your loop. Cool. And then the other approach was bottom-up. This is the one that I think I gravitate to. It's a bottom-up approach. You define dp of I as some function of previous dp's, and then you have base case at the beginning, and you return the last item. So these are the two main approaches. So let's say you were climbing stairs, and let's say we were doing this problem. You can either climb like 1 or 2 steps, or return the number of distinct ways to climb to the top of the staircase. So if n is equal to 2, then your output is 2, because you can do 1 plus 1 or 2. Then n is equal to 3, and your output is 3. Because you can do 1 plus 1 plus 1. And then you can do 1 plus 2, and then 2 plus 1. Right. So this one doesn't seem too bad. The main question here is, what do you define dp of I as? And dp of I probably could be something along the lines of how many different ways can we get to this graph? So then dp of I would equal to dp of I minus 1 plus 1, and then plus dp of I minus 2 plus 1. I imagine that's it. So it would need some sort of unloaded map to keep track of memorization, probably a better name for this. And then I was just double checking if that's commented out or not. So if mem of n does not equal to 0, would it be 0? Let's do this a bit more accurately and just say our count of n does not equal to 0. Then return mem of n. Otherwise return mem climb stairs of n minus 1 plus climb stairs n minus 2, and then plus 2. Up here we also want to check our base case. So if n is less than or equal to 0, and you return 0. And that might be it. Let's have a look. Wrong. Why is it wrong? Oh, maybe you have to subtract 2 from here instead. 4 instead of 2, and then here a instead of 3. Well, let's walk through it. So, well, actually this shouldn't matter, because this is just for memorization, but regardless, we could do this. Yeah, it doesn't change anything, man. So if you pass 2 in, then 2 is not less than or equal to 0. Your count is not equal to, is equal to 0, sorry. Yep. And then you find the mem of 1 and then the mem of 0. Okay, so if you're below 1, then you should return n, because I think the problem is that, oh no it isn't, that for 1 you're returning 0 and then you're going through this and then saying 1 is equal to 2 when it's not. What's the issue here? N is equal to 2, my output is 3. So if I pass 2 in, then 2 minus 1 is 1. So it calculates time stays of 1, and then 0. So then for 0, it should return 0. And then for 1, it should return 1. So it is meant to be returning 3. So what's wrong? Well, I'm effectively saying that to get to level 2, you can either go to level 0, maybe you can go to level 0, however many ways you can get to 0, and then add 2, where you can get to level 1. Right, that doesn't make sense. Maybe it should just be this. Maybe return a constant 1. Yep. Right. Well, okay, yeah. There you go. Right. Cool. So then house robber. What was this? You would say vector of int dp is nums.size plus 1. And then you start at 0. And you would define dp as the max you can rob at a house. So for int I is equal to 0, I is less than or equal to nums.size plus plus. And then you would just say dp of I is equal to, you want to start at 1 actually, is equal to dp of I minus 2. Oh, okay. Is equal to the maximum of dp minus 2 plus nums of I, or dp of I minus 1. Now the problem is that I minus 2 is minus 1. So we'll probably just start at 0. I mean, what's an elegant way to do this, buddy? What's an elegant way? Come on, think. Okay, sure, we'll do this plus 2. And then plus 1. And then this has to be minus 2 actually. Yeah, and then return dp of nums.size plus 1. Right, I believe that this will work. And it didn't. Oh, okay, small typo. Yep, so this is bottom-up approach. and we memorized. Oh, what did we do? Okay. Can't tell if I'm stupid, but oh, this is the one they gave us. Should you memorize something of size and start at -1? If I is larger than size, then you return 0. No. If mem of I is not equal to -1, we return it. Otherwise, mem of I is equal to this plus this. Yep. I plus 1. I plus 2. Very strange. It's like they're going in reverse. Oh no, they're doing top-down approach. So they're passing into TFS and trying to solve the maximum they can make here. Right. Oh, so they are going in reverse. Okay, interesting. What is that? Am I doing the same thing? Oh, I am. Okay. I think I must have copied the answer then. So then the difference here is that they're arranged in a circle. What changes about your algorithm here? What changes is that you can't indiscriminately pick the first and the last house. So at the very end, you need to make a decision between robbing how do you even do that? I don't even remember. You can't even make a decision on if you rob the next one or not, because you don't know if it's included or not, so you don't know how much money you're losing out on. Alright? I guess let's go back to our fundamentals, see if we can get some help with that. So the fundamentals are that with DP, you need a base case and you need a recursive case. So our base case is DP of, let's say, -1 is equal to 0. So at the beginning, you can't have made any money. And the DP of anything below 0 is equal to 0. So then your DP of I is equal to the max money you can make up until this point. But then how do you keep into account this? I'm not too sure. Perhaps you could draw a decision tree. At each step, you either rob the current house and skip the next one, or skip the current house and move on to the next. Okay, sure. So, decisions. So, you can either rob, if we're focusing on the first example, rob this house, have the money from I -2, and don't rob this house. Keep money from I -1. Okay. I suppose you have to make two assumptions. Either you rob the first one, and then you try to find the max DP, and then you rob the second one, and then you find max DP from there, and then you find the maximum of those two. Is that the answer? Yeah, there you go, exactly. Whoa, we got it. Yes. nice. Very cool. We got it. I'm just looking at these again to warm up my brain because I haven't done dynamic programming in a long time. Return the first number of coins you need to make the exact target amount. It is impossible to make return -1. So 12. Note that we do not have to use every kind of coin available. Coins 2, 3, coins 1. Okay, cool. So how do you even go about doing this? I have no idea, so let's go back to our base case, our fundamentals. So our base case is I don't know. So you need some sort of something for dp of I, right? Where dp of I represents something to do with the closest that you can get. So, okay, how do you go about solving this? Well, you need some sort of sequence of decisions, right? What are these decisions? The first decision I would have to make is which coin do I include, right? So do I include 1, 5, or 10? So I would probably include 10, right? And then you have to make a decision on what the next thing you could do. So you would only be able to make 11 and then 12, right? But then what if you have 4 and 3? Let's say you have 5 and 2 and you were aiming for 11. Well, first I would say, okay, I want 5, and then I would say I want 5 again, and then you can't add 2, right? So then I would have to somehow go back and say, can I try 2, 2, and 2? Okay, but that doesn't work. So let's see if there's another approach, another way of thinking about this. Bottom up and top down. So bottom up works by building it sequentially like we are now. Top down works by asking a question of, okay, I know that this thing is a function of other things, etc. Go figure out what those are. So I really don't know what the thing might be. Breadth first search. Think of this problem in terms of recursion and try to visualize the decision tree, as there are multiple choices at each step with a given amount. At each step of the recursion, we have n coins and branch into paths using coins that are less than or equal to the current amount. Can you express this in terms of recurrence relation? Also, try to determine the base case to stop the recursion. In terms of recursion, and try to visualize the decision tree. Okay. So losing coins. Okay, so the decision tree would look something like this. The first decision you'd have to make is, what's the first coin that you add? Right? So the first coin you can add is 5, and then 2, and then 1. And then what's the next coin that you can add? Here you can add a 5, or you can add a 2, or you can add a 1. here, let's assume that you can only add 2, right? Otherwise, you would have explored 5. You would have explored 5 and 2 together down this path. And here we can only explore 1. And then going on, here you explore okay, so 2, and then 1, and then 1 again. And then here, 2, and then 2, and then 1. Okay, I think I'm getting carried away. And so on, like 1 here. Whatever. Now, the important thing is, how do you make a decision on what the value is? Well, the value, if you remember, or the question that we're trying to solve in the first place, is what's the minimum number of coins that we need? So, how would you represent that here? How would we solve that? Well, obviously the minimum number of coins is 2 here, right? So I guess maybe the question can be, using 1 coin, how close can we get? And here the answer is 7. And then the next one is, using 2 coins, how close can we get? And the answer here is 10. Oh, why did I say 10? 7. So, yeah. And then here, using 3 coins, how close can we get? Well, we can get 12. But let's go to my other example really quickly. So 5, 5. Well, let's do 4, 4. And then let's do 9. That doesn't work though. What was the example that I used? Okay. Well, this works. 5 and 2. And then your goal is 11. So this breaks the expectation, because it breaks our current algorithm, because you have 5 and 2. And now here you would try add 5 to make 10, obviously. And then here you would add 2 to make 7. And then here you would keep adding 2. 2, 2, 2, 2, 2. And so on. So the question here would be, how close can you get? Well, we can get 5. And then here, how close can we get? Well, we can get 10. And then the next question that you would ask is, well, how close can you get now? Well, we can take this 10. It's the only value we can see, so there's not much you can do. Or you can go back up here and add 2 2s. Interesting. What's the next hint? If the amount is 0, we return 0 points. The recursive relation can be described as the minimum of 1 plus the amount minus the coins of I, where we return the min number among all parts. Oh. Oh, okay. This makes a minimum of 1 plus road creative 1 plus the DFS of all the coins, right? Amount Oh, okay, that's really intelligent. Wait, so was I close at all? Right. The question should be not what can you do on each layer, but given you have this much remaining, how much? Right. Given you have this much remaining, how many coins do you need to make it work? Right, okay, cool. So your DP of I is equal to the minimum of 1 plus the DFS of 1 minus the DP of all your coins. Sorry, not DP. Yeah, coins. And then what's the amount here? I guess just amount, right? Like you pass it down DFS. So you would have some sort of main like this. And then you'd have a DFS. This DFS takes an amount, and it takes coins, and it takes DP. All it says is if DP of I guess I is amount? I'll call this remaining. So if the DP of remaining does not equal to -1, then you return whatever that is. Otherwise, you want to solve for the DP of this. So we say DP of remaining is equal to the minimum of 1 plus the DP of all your coins. Cool. Let's do it. So your vector of integers is size enough with a default value of -1. And we want to make a private method where we do a DFS. And we want to pass in the coins. We want to pass in remaining. We want to pass in beautiful DP vector. And what else? I think that looks like that. So what exactly does DP of I represent? Like, let's say we had DP of amount. Well, I suppose we should do that, right? So DFS coins remaining is amount and then DP. And then you return DP of amount. That makes sense. Now what? We already wrote it out. Why are we waiting? So if the DP of the remaining amount is less than larger than or equal to 0, then we can just return that. Return DP of remaining. However, we also want to integrate our base cases. If remaining is less than or equal to 0, then we could just return 0. And that's also. Otherwise, DP of remaining is equal to result. Return a result. And what we can do here is we say DP of remaining, int result is equal to the minimum of let's say int max, and then for int coin in coins, result is equal to the minimum of result and 1 plus dynamic depth first search, remaining minus coin, and then DP. Perfect. Is that it? No. We can't return values. Is this true? No, we definitely should be able to return values. Why do I think that for DFS you don't return values? I guess sometimes you don't, right? Yeah. Yeah, I suppose. Sometimes you don't. But you definitely do need it in this situation. So actually, remaining should it equal to... Huh? What's the problem? Oh, maybe that's the problem. Ah, okay. And then... Ah, okay. This should actually return 0. If remaining is less than 0, then you return -1. Right? Because it's impossible to get to that point. If result is equal to what? With -3, min found is equal to min of min found as a result. Okay. What's... Oh my gosh. Okay, I really need to pay attention. That's not very good. Oh, now did both of these return -1? No. But this one does. I suppose if you return... If it's into max, then you want to return -1. Otherwise you can just return min found. And then you don't need to do the logic twice. Okay, I'm getting tired, but I kind of want to know the answer. Recursion, dynamic programming, top-down. Yeah, that's what we're doing. If the amount is equal to 0, return 0. If you can't find it, then return... If you can't find it, result is this. If the amount... Yes. I should have done that check, actually. Okay. Okay, I'm getting tired. Please let me wrap this up. dp of remaining is larger than or equal to 0. Okay, I'm gonna dial in. We're gonna reject the sleepiness. Int coins if result int result is equal to whatever. Int max. Yes, this matches the max's min of res, and then 1 plus res. That's exactly bar for bar what I'm doing. Blood. What could it possibly be, bro? I'm very lost. Oh my, no way. Brother. Okay, that's not even it. Thank you. Thank you for ruining my life. Oh, time limit exceeded. Even better. Output minus whatever billion. Well, yes, this does make sense, actually. Alright, I gotta work here before. Thank you for reminding me. Was my previous submission using an uploaded map? Oh, okay, sure. That's very similar. I need to get this one working. It's my life goal. Amount. It's literally the exact same. I suppose the only thing that is different is that this is not 0 initialized. What could it possibly be? Int max. I can't take it anymore. Give me the answer, buddy. Alright, we are back. We did find the issue, I believe. Another issue. Very funny. Very funny. I'll give you props. dp of remaining is equal to the minimum found. The minimum found should be 0. Because you should get past here. And then you should be able to go with the 1 coin. And... wait, what? Alright, I would like to save Claude once again for saving my brain. We had a minor issue. Wow. 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 That is very bad. It's terrible. But I suppose it might have something to do with using an array here. But you might not need to. That's very, very bad. We could actually, I don't know how you fix it, other than using a hash map. Is it even easy to do that? Let's see. And then you just do unordered map. And if dp.count remaining is larger than 0, is that it? Oh. Okay, I don't know why it doesn't work. I'm not here to solve this problem. I didn't realize that this was going to take so long. We are here to solve this problem. Alright, let's take a stab and see if I can get it. You're given an array of distinct integer numbers. Bro. You're given an array of distinct integers nums and a target integer target. Return the number of possible combinations that add up to target. Test cases are generated so that the answer can fit in a 32-bit integer. So if you have the numbers 3, 1, and 2, and your target is 4, you can make 1, 1, 1, 1, 1, 2, 1, 2, 1, 1, 3, 2, 1, 1, 2, 2, and 3, 1. Wait, this doesn't seem too bad. Famous last words. Very famous last words. So 1, 2, 3, and your target is 4. Bro. Alright, boom. Welcome back. Okay, so as I was saying, this seems very doable. So it's a combinations question. But it's backtracking. Right. Sorry, it's dynamic programming, not backtracking. I got excited because I thought it was backtracking. So you could kind of choose it. You could get it pretty easily. Wow, okay. How do you do DP? So base case and recursive casing. So with the coin question, our base case was that if you had to make 0, then you get 0. Like you need 0 coins to do that. Our base case is going to be that if what remains is 0, then you need 0. You can only use, like, you can't add more to this, so return whatever this number is. That doesn't make sense, right? You know, we can't return that. So I guess the question would be instead, base cases, if what remains is 0, then return 0, which represents the extra you can add to the set, right? So maybe we're aiming for 4, right? So you ask yourself, oh wait, this is very similar to the coins question. You ask yourself, how can you make 4? Or you can make 4 by taking a 1 and then adding a 3, or by taking a 2 and then figuring out like 2, or you can take a 3 and add a 1, right? So then you ask yourself, how many ways can you make 3? Well, to make 3, you can take a 1 and make a 2, and add 2, or you can do the same here. Sorry, what do I mean by that? I mean, or you can take a 2 and then add a 1, or you can take a 3 and add a 0. And then if you get to this point where you now need to consider, like, okay, how do you make 2? Well, you make 2 by adding a 1 to a 1, or a 2 to a 0, or a 3 to a -1, but that -1 is impossible. So you quit. Alright, perfect. I think I got this. I think this is light work. Light work, champion. So we're gonna not make the same mistake, and we will use an unordered map today. And it will be great. It will be awesome. And we can call it memo, like we've slowly learned to do. Then we can say, Is it cheating to look at the answers for previous questions? Maybe, if they're this close, but I don't care. Have you considered? I don't care. Combination sum, where is this? Here. So the one that I was looking at is coin change. For each coin, right. It's similar but different. I guess I want to do it a DFS search here, where you pass in memo, you pass in the numbers. I think top down is a bit more intuitive here to me, and whatever remains. So the base case is if remains is equal to 0, we return 0. Then you say if memo dot count of remains does not equal to 0, then you return memo of remains. Otherwise, you can iterate through the numbers. And if the number is smaller than whatever remains, not smaller, larger, then you return. Otherwise, you search that too. So remember, nums and remains minus num. And whatever that returns, you do is sum plus is equal to. And then you tell yourself that member of remains is equal to member or member res, and then you can return member of remains. Intro res, go to numbers. If number's too large, boom. Member, nums, and then target. And then int result is equal to that. And then you can just return result. Is that it? Not quite. It's never that easy. Member, nums, and remains minus number. What's wrong then? Oh. Unordered. Unordered what, bro? What are you unordering? Unordered map. Map. There we go. Let's see. Sum was not declared in this scope. That is true. It's right. Interesting. Very interesting. Right, because you need to add one, I believe. Is it double every 10? Or is it that you return one here? No, it can't be that. Wait, what? It is? Oh my gosh. Wait, why? The way that you can make 0 is using a single set, the empty set. The way that you make 1 is with a single set of 1. The way that you make 2 is an empty set plus 2. Or 1 plus 1, 2. That kind of makes sense. Okay, this is the first time in a long time that intuition carries me across the border. Across the border? What's the word? Across the finish line, right? Helps me get there in the end. Let's see what the intended solution is. Yep. A break It's supposed to have to sort it, yeah. And then bottom up, so they have to use a long in case they overshoot. I don't care about that one. Bottom up too, I also don't care. Cool. Very cool. I'm not super happy that it's so inefficient. What's the good one? Wow, so as soon as I decide to use a hash map instead of vector, now they're like, oh, vector is now the optimal solution. Okay, buddy, whatever. I guess it just means that what does it mean? It means that the values for target are much lower in this one than the other one. Let's see if that's true. So target can only be under 1,000. And then, what was it? Coins.size? No, amount. We were using amount. Yeah, and that can go up to 10,000, but this is only 1,000. Oh, interesting. Okay, so if it's up to 1,000 and you're using DP, interesting. If it's up to 1,000 and you're using DP, good. Come on, give me the thumbs up emoji. Alright. To use vector, if more than 10,000, use hash map. Cool. Alright, well, that's today. I'm happy I was able to solve the last one pretty quickly. Definitely need to practice dynamic programming a little bit more. I think more importantly, the brain fog needs to be eradicated, in the sense that I just stop thinking sometimes for no reason. I'm much happier with code clarity. I'm happy with slowly less filler words. My thinking is a bit more structured, less frantic. Yeah, those are two issues. I think also holding more context in my brain would be useful. It's just, I am tired right now, but this is something that I always struggle with. I guess timing of speaking is pretty important. So commit to saying something and finishing the sentence, and then do whatever you need to do and then move on. I think that's a good, like, not being able to do that properly is an indicator that your brain is all over the place and you don't really think too structured. I'm pretty happy with this, and I'm happy that I'm slowly approaching the fundamentals instead of just relying on heuristics / intuition. Yep, I think, yeah, I'm pretty happy there overall. I'm excited for day 5. Day 4? Day 4, yeah.